Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on semiconductors. Last time, we learned a great deal about vacuum tube devices. These are devices that rely on vacuum tubes to conduct electric currents. Today, we will learn all about semiconductors. Let us begin. In Unit 3, remember that we learned that materials can be divided into 3 classes based on their ability to conduct electricity. Insulators, such as glass, rubber, and plastic, do not conduct electricity. The electrons in these substances are tightly bound to their parent atoms. Conductors are materials that allow electricity to flow through them. This is because the electrons in the outermost shells of conductors' atoms are free to move around. We say these electrons are in the conduction band. Most conductors are metals. Finally, semiconductors conduct electricity less well than conductors, but much better than insulators. In semiconductors, only a few of the outermost electrons can break free from their parent atoms. But the interesting thing about semiconductors is that more electrons move into the conduction band when the semiconductor is heated. Because of the tightness of the bonds between its atoms, we know that diamond is an insulator. Because of the looseness of the bonds between its atoms, we know that graphite is a conductor. Germanium and silicon are semiconductors because they have materials with electrical conductivity due to electron flow. They have an intermediate magnitude between that of a conductor and an insulator. So are materials such as lead sulfide, selenium, and gallium arsenide. Students, I would like you to test your knowledge of insulators, conductors, and semiconductors. From this list, please classify each material.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back. Students, did you find the exercise challenging? Let us discuss the answers. We heard earlier that diamond is an insulator. Silicon is a semiconductor. Paper is an insulator. So is glass. Copper is a conductor. Wood is an insulator. Aluminium is a conductor. Germanium is a semiconductor. And brass is a conductor. We have a name for germanium and silicon and other naturally occurring semiconductors. We call them intrinsic semiconductors because their conductivity is not affected by external factors such as magnetic fields. Intrinsic semiconductors conduct current well at high temperatures, but they are less efficient at low temperatures. This is because covalent bonding between the electrons is very strong. As the temperature of these semiconductors rises, some of their atomic bonds are broken, and electrons become available for conduction. As the electrons leave the metal, their absence is represented by something called a hole. A hole acts as a positive charge into which an electron can flow. To make semiconductors more efficient, scientists conduct a process called doping. Doping is the process by which impurities are introduced into a semiconductor to change the material's electrical properties. Doping introduces extra charge carriers into the semiconductor's atomic structure so that the material can carry stronger charges at lower temperatures. When scientists conduct doping, they produce extrinsic semiconductors. Dopants, which are the impurities added to extrinsic semiconductors, are classified into two types: donor impurities and acceptor impurities. Donor impurities donate excessive electrons to semiconductors for conduction. Impurities such as antimony, phosphorus, and arsenic are donor impurities. We have a name for extrinsic semiconductors that have been doped with donor impurities. They are called N-type semiconductors because more than half of the carriers inside the material are electrons. N-type semiconductors are said to have electrons as their majority carriers and holes as their minority carriers. When bonded with semiconductors, acceptor impurities create holes that can accept electrons. Boron, gallium, and indium are acceptor impurities. We call extrinsic semiconductors that have been doped with acceptor impurities as P-type semiconductors because they have more holes than electrons. P-type semiconductors have holes as their majority carriers and electrons as their minority carriers. Students, on the periodic table of the elements, you will notice that silicon and germanium are located in group 14. Please take a few moments now to map the following donor and acceptor impurities on the periodic table. What do you observe?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back. I hope you found this exercise enjoyable. When you mapped these elements on the periodic table, what did you discover, students? You should have noticed that antimony, phosphorus, and arsenic all belong to group 15. This is because each has one more electron than the semiconductors in group 14. You will also have noticed that boron, gallium, and indium all belong in group 13. These elements have fewer electrons to give and when bonded with a semiconductor, create holes. When we join p-type semiconductors with n-type semiconductors, interesting things happen. The two substances immediately create a bond. At the junction where they meet, some of the n-type's electrons drift across into the p-type's holes. This movement is known as diffusion current. And you will learn a lot about diffusion current in another lesson. Students, teacher, I am sorry to say that we are out of time for today's lesson. To review, we spoke a great deal about conductors, insulators, and semiconductors. We learned about impurities and doping, p-type and n-type semiconductors, as well as intrinsic and extrinsic semiconductors. That is a lot to learn. Until next time, thank you, teacher. Thank you, students.